Welcome to lesson 18, limits at infinity and horizontal asymptotes. So we have spent some time looking at how the first and second derivatives of a function describe the shape of the graph of that function. So in our next step, we're going to talk about end behavior. If a function has an infinite domain, at least goes on in one direction forever, we need to know what's happening to the graph as x values get either really, really large or really, really small. So in this lesson, we're going to define limits at infinity and show how these describe graphical behavior. We'll also look at a few ways to calculate these limits. So let's start with the definition of what we mean when we say take a limit as x approaches infinity. So our first definition will start with let f of x be defined on an interval a to infinity. So it doesn't matter what the a is, but it's defined for all numbers greater than a certain number. Okay. Then the limit as x approaches infinity of f of x equals L means that f of x can get as close to L as you want. And that was the same lingo we used when we first introduced limits, but when we did them before, we were approaching a number here. So then the next thing we would have said was for x values close to that a. But since we're approaching infinity now, we're going to say as x increases without bound. So as x approaches infinity means as x gets bigger and bigger and bigger forever. If that limit actually exists, that means the y values are getting closer and closer to this number L. And then we'll just do the same idea, but in the negative direction. So almost identical definition. Let f of x be defined on negative infinity to a. So this time for everything less than a particular number. Then the limit as x approaches negative infinity of f of x equals L is basically the same thing, except for this time x will be decreasing without bound. So means that f of x can get as close to L as you want as x decreases without bound. So it becomes more and more negative. All right, so I think probably some pictures are going to help us visualize what these things are saying. So we have placed down here to draw some functions. So let's see. Let's start off with maybe just something simple, kind of like a exponential type function, type graph, type shape. And it's going to have this y value L that the graph gets ever closer and closer to. So as x approaches infinity means x goes off in the positive direction, this f of x is going to get closer and closer to this line L. So that would be a situation where the limit as x approaches infinity of f of x equals L. And we'll draw another one, maybe something, the function does something else, but then sort of oscillates down. And again, that y value, that right there is, we're going to call L. So same thing. the limit as x approaches infinity of f of x in this case is also L. You'll notice that it does have a little oscillation, but it damps down and still can be made closer and closer to that value of L. And then we could do a similar thing just in the negative direction. So limits as x approaches negative infinity. Maybe we might have something like this. And again, there's that L value. So this would be the limit as x approaches negative infinity. So just going off in the other direction, the negative direction, these y values are going to approach this one number L. And last but not least, I mean, we could always have something like this, and it could actually be that it's the same limit in both directions, or we could have different ones. And this also has the limit as x approaches infinity. Okay, so a couple of visual aids just to give you a way to kind of wrap your head around what those definitions are meaning. And when you look at all of these pictures, what is the phrase that you want to use to describe what's happening here? I mean, in pre-calculus terms, what are you looking at? You're looking at horizontal asymptotes, right? So we're just going to redefine horizontal asymptotes as basically lines where the limit as x approaches either infinity or negative infinity is equal to that number. So that's our next definition here. Okay, the line y equals L. So that's going to be a horizontal line, is a horizontal asymptote of y equals f of x if, and so you can either have the limit as x approaches positive infinity of f of x be L, or you could have the limit as x approaches negative infinity of f of x be L, or you could have both, but you only need one in order for a line to qualify as a horizontal asymptote. So if you think about it, how many horizontal asymptotes can a function have? I mean, it's certainly possible for there to be zero. I mean, just take a parabola, right? There are no horizontal asymptotes there. Or you could have one, like in the last picture on this page. Here, we've got one horizontal asymptote, actually, in pretty much all of these pictures. But what if maybe this was just moved down and was here? So then I would have this one on the left and a different one on the right. So our last option is 2. But you only have 2 ends. You only have a positive infinity and a negative infinity, so you cannot have more than 2 different horizontal asymptotes. Okay, so we've actually just kind of introduced the last type of limit that we're going to look at in this class, which is limits at infinity. And so this first example is just kind of reviewing some limit stuff. So go ahead and pause and fill in your answers to each one of these. Okay, so let's take a look at what we got. The first two are asking us about this end behavior, this what's happening as x is approaching infinity. So as x is getting bigger and bigger, what does this curve appear to be doing? Now, granted, we could use a little bit more information here, but we're going to go ahead and just assume that it's kind of approaching this line here, which would be at -2. And similarly, on the other side, as x approaches negative infinity, so it goes off forever in this direction, we're going to assume this becomes a horizontal asymptote, so that the limit as x approaches negative infinity would be 2. Then just looking at a couple of our older school limits as x approaches 1, so that would be from both sides. On the left side, the curve is going up, and the right side, it's also going up. So we've got a vertical asymptote here. And since both sides are going to infinity, we would write that that limit is infinity, even though it technically doesn't exist. And similarly, as you approach 3, you have on both sides the curve going down to negative infinity. And so if you wanted to just write the equations of the asymptotes, horizontal lines are y equals and vertical lines are x equals. All right. And then one more example here, just kind of leaning into some pre-calculus knowledge. You should know what the graph of 1 over x looks like. That's the hyperbola in the first and third quadrants. And so once we see that, we can realize that the limit as x approaches positive infinity is 0, and the limit as x approaches negative infinity. Okay. We are using limits to describe these horizontal asymptotes. So limits as you go to infinity or negative infinity is what describe horizontal asymptotes. And both of those are 0. Okay. It's kind of a little bit of an intuition too to think about this. As x gets bigger and bigger, 1 over a really big number gets really close to what? 0. And it doesn't matter if that number is either positive or negative, 1 over a really big negative number is still getting really close to 0. It's a very, 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 very small fraction close to 0. Okay, so the next one asks us to sketch the graph of the function of inverse tan of x, which you probably don't remember. And then again, use limits to describe the horizontal asymptotes. So I will remind you about this function. It looks like this, and it has these boundaries at these y values. Okay, so this is y equals inverse tan of x. And so again, if we're just using the notation, the limit as x approaches infinity of inverse tan of x is pi over 2. And the limit as x approaches negative infinity of the inverse tan of x is negative pi over 2. So again, just trying to add a little intuition, mathematical understanding of what's going on. If I'm doing an inverse tan function, if I'm plugging in numbers that are getting bigger and bigger and bigger, then the inverse tangent of that is going to be pi over 2. Or if they're getting smaller and smaller and smaller, then the inverse tan of that will be negative pi over 2. If you think about a tangent graph, right? Tangent does this, and this was pi over 2, and this was negative pi over 2. Think about it that way. As your numbers get closer and closer, your angles get closer and closer to pi over 2, the tangents get bigger and bigger. So if you plug in bigger and bigger numbers to the inverse, you're going to get closer to pi over 2. Okay. So then just going to talk about a couple of limit laws that we applied in lesson 4. So all of those limit laws do apply to limits at infinity and negative infinity. So for example, and this first one is going to be really important for us as we go through some techniques later in this class or later in this lesson even. If we're doing the limit and we have a constant, we can pull that constant out front. Remember that. And furthermore, since this is 1 over x to the n, remember it's really like 1 over x all to the n. We can pull that power outside of the limit. So we can do the limit inside first and then raise that to the n. Now, didn't we just on the other page, the previous page, looking at a graph, evaluate the limit as x approaches infinity of 1 over x? And what was it? If x gets really, really, really big and it's 1 over that, then that's going to go to 0. So this whole thing will go to 0. Okay. And that would not change if this was going to negative infinity. So also the limit as x approaches negative infinity of c over x to the n will also be 0, because it's this step right here where the 0 comes in. And we know that that limit is the same no matter which way you're going, positive or negative infinity. So this is a very, very useful, I'll just put a plus minus here so you can identify that it's either one. Very, very useful. If you have a number over a power of x, and that's going to either positive or negative infinity, that whole thing will go to 0. And that should make some logical sense. Again, any constant divided by something really big is going to end up becoming very close to 0. So similarly, we could apply those same limit laws. Remember, we can take the limit of the first term and then subtract the limit of the second term. Whoops, forgot my limit. And we just did this above. This is a constant over x to a power. So that's going to go to 0. And what's the limit of a constant? It's just the constant. So pretty straightforward applications of the limit laws.